Hello YouTube, today we're going to be doing a problem involving satellites, which is pretty cool in physics. So we have a 1,000-gram satellite placed in geosynchronous orbit, which means at the same distance above the same location on the surface of the Earth as at all times. At what distance from the surface of the Earth must it orbit? Okay, so being in geosynchronous orbit gives us a few pieces of information, but first let's write what we know. Well, we know the mass of the satellite is 1,000 grams. Now, being in geosynchronous orbit means that as the Earth rotates, the object is rotating at the same rate as which, or at the same time as which the Earth is rotating. So that means their period is in 24 hours. The Earth rotates 24 hours in one day, full rotation. That means same thing with the satellite. Now, when we're doing our calculations, you're might want to convert the hours into seconds, so we'll do a conversion here. 1 hour is 3,600 seconds, and that's 86,400 seconds is 24 hours. So, let's draw a picture. So, we got the blue circle there will represent the Earth. RE in green represents the radius of the Earth, which is given. And that brown dot there is the satellite. And we want to know what distance from the surface of the Earth must it orbit. So that's in D. But when we're doing gravitational calculations, we're going to be using this radius of the orbit. So from the center of the Earth to the object is that radius that we're going to be using for our calculation. So we're actually going to be looking for that distance in red, which is the radius of the orbit, the total radius, minus the radius of the Earth. So keep that in mind. That's a really key component. Now, the formula we're going to be using, since we're dealing with the period here, is going to be this period equation. But we're looking for the radius, right, of the object. That's something we can solve for. So let's solve for our O. Now that looks kind of funny when you do all the algebra, but once you simplify it, it should look something like this. And when you just solve for R, so that's algebraic steps there for you. Now you simply just plug in the information we know. So we have, I put G first, so that's G, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, times the mass of the Earth, 5.92 times 10 to the 24th kilograms, times the period squared, which we calculated to be 86,400 seconds, all that over 4 pi squared, take that to the 1/3 power, or cube root it, and you get a radius of 4.24 times 10 to the 7th meters. Okay, so now we have that larger radius, but that's not what we're looking for. We're looking for the distance from the surface of the Earth. Well, we know this distance is the radius of the orbit minus the radius of the Earth. So here's the radius of the orbit minus the radius of the Earth, and that gives us the actual distance from the surface of the Earth, or above the Earth's surface. Cool. So let's move on to the next portion of the question. If the same satellite is brought to a new circular orbit with half the orbital radius, what is the new period? Okay, so that's the two pieces of information we need to worry about, half the orbital radius and the period. So half the orbital radius will simply be 1/2 r, or around half the orbital radius. And the period is t. So that's what we're looking for, and we have a new condition. So we're going to use that same formula, put it in this condition here again, but now instead of r being just r sub 0, or r0, radius of the orbit, we're going to make that 1/2 r. So that's the only difference we're doing. Just making it 1/2 r0, because that's what it's saying. The condition, the radius got smaller by half, so it's half the radius. So simply plug in those numbers again, and use that 4.24 times 10 to the 7th, because that's the radius of the orbit. We're not looking at the distance, we're looking at the radius of the orbit, which is in black there. So make sure you use that number. That's one mistake that I can see people making. And then take the square root of G times the mass of the Earth, and you'll get 30,724 seconds. Now you want to know how many hours that is, so you can convert it, and that's 8.53 hours compared to 24. If you notice, that's a factor of 4 difference, which we'll get to later. Okay, next problem. Part of the problem is compare the orbital speeds. Okay, speed meaning velocity, so we're going to divide up the problem here into the two orbits. So we're going to be using this formula here. The velocity is equal to the square root of gm, mass of the Earth, over r. So I'm just going to divide up to v1 and v2. So the first object, velocity of the first object, you simply plug in the information from the problem. We calculate the radius of the orbit back here. That's just what we're going to be using there. But for the second orbit, remember, oh wait, one second. And then Sorry about that, got distracted. So you just plug in the numbers there, and you get a velocity of 3,065 meters per second. Now we're just going to do the same thing. We'll solve for the velocity, except remember the second orbit is half the radius, so simply plug in half that number, do the same calculations. Now you get 4,335 meters per second. Now, what does this tell you? That means the closer you are to the Earth, you're going faster, right? Because if you're half the orbital radius, you're going to be going faster. Now we're going to take another look at that in terms of forces. It says, how does the force due to gravity of the Earth acting on the satellite change between the orbits? Well, the force of gravity is G times the mass of the Earth times the mass of the object over the radius squared. Orbital radius, keep in mind. So we'll just divide it up again, force 1 and force 2, just like the velocities. But remember, the second one is half the orbital radius, so same calculations. And remember, the mass of the object was from the first problem here. We said the given information mass of the satellite was 1,000 grams. I guess I should make that mass of the object to be consistent, but for the sake of the formula here, we'll just use that. Simply plug in that. Something happened, I don't know, you get 222 newtons, and then same thing again, except you do half the orbital radius there, and you get 886 newtons. So that means the closer you are to the Earth, the more newtons are acting on you, more force. Okay, so that's pretty much the problem here. Hope this helped in terms of doing a nice gravitation practice problem. I love satellite problems and talking about rocket science. It's kind of just some aspects of it, but it's kind of like the introductory to it. So I thought this would be cool to go over. I hope you enjoyed the problem, and good luck practicing.